Alright, so this section covers section 12.4, and we're basically going to be learning all the different ways and techniques that we can use to solve both exponential and logarithmic equations. The first two that we'll look at are two that we've already learned how to solve, so these are more review problems. Notice that in both of these next two problems, I can write both sides of the equations as exponents where they have the same base, because this left hand side has a base 4, and 16 can be rewritten as an exponent with base 4, specifically 4 squared. And once we have the same base, it's plain to see that the only way 4 to the x can be equal to 4 squared is if the powers are equal. So x has to be 2. Now I can do the same thing with the next one. What base should I use though if I have 4 and I have 8? Well, 4 is 2 squared, right? 4 is 2 squared, and 8 is 2 cubed. So this can be rewritten as 2 squared to the 2x plus 1. And then the right hand side can be rewritten as 2 cubed to the x plus 4. And then remember our power rule. When we raise a power to a power, x to the m raised to the n power, what do we do with those powers? We multiply them. That's m times n. So here we need to distribute this 2n to the 2x plus 1. So this would become 2 to the 4x plus 2. And on the other side, if we distribute the 3n, we have 2 to the 3x plus 12. And now that the bases are the same, we can set the powers equal to each other. So we can set 4x plus 2 has to be equal to 3x plus 12. And solving from there, we get the x's on one side and the numbers on the other. We end up with x is equal to 10. So those are basically review problems, but what do we do when we're trying to solve an exponential equation where the bases are not the same? For this next example, we're going to need a different tool to use, something we haven't seen before. What we want to start off first here is notice that this example is an exponential equation, and the very first thing we're going to want to do in equations like this is we're going to want to isolate the exponent. So how do we do that? We've done this many times. We're going to go ahead and add 7 to both sides. Now when we add 7, it cleans things up a lot. The left hand side only has the 5 raised to the x minus 7 power, and then the right hand side becomes 20. So let's go ahead and make a little note here. These exponential type of equations, just like we've seen with many equations so far this semester, we want to first isolate the exponent. First isolate the exponent. Good thing to remember. Okay, so now we got this problem, and what you're going to notice is this one cannot be solved with the techniques that we've done before for exponential equations. The two examples we just looked at, both A here, we could make this an exponential equation where both sides had exponents of base 4. This one here, example B, both sides had exponents of base 2. We could get the bases the same. Now in this example, notice that the left side has an exponent with base 5. Can I take 5 to some power and have it be equal to 20? Of course, we know the answer to that is no. We can't do that. So we're going to have to use a different approach. Now, we could use the rule that we had a couple sections back. We're changing between exponential and logarithmic form. But a lot of times, especially when going this way in that little rule, a lot of times students get mixed up with that. So I'm going to show you a new tool. And what we're going to take advantage of is the power rule that you learned in the last section. So if you remember the power rule, let's go ahead and write that down. Power rule says that if I had a log raised to a log of x raised to some power r, and let's say the base is b, then what I can do is I can take that power r and I can move it to the front as a product. And so what we saw is that this could be rewritten as r times the log of x base b. And this works for any log. Let's make a little note of that. This works for any log, whether that's log base 5 of x, or natural log of x, or the common logarithm. Remember, if we don't write the base, that's log base 10. It works for any log, which is nice, because that means we could use it in this case. But the problem we have here is we can't quite apply it yet because we don't have any logs in this example. We have an exponent. Well, many times when solving equations, we get used to this idea of doing the same thing to both sides. Let's try, in this case, taking the log of both sides. Or specifically, let's take the natural log of both sides. So if I do that, let's go ahead and make sure that looks like it's on the side. Let's take the natural log of both sides. Take the natural log of this side and take the natural log of the other side. So when we do that, this becomes the natural log of 5 to the x minus 7 power and natural log of 20. Give yourself a second to kind of let that sink in. All we're doing is taking the natural log of both sides. We're applying an operation. It's just like adding 7 to both sides like we did in the first step. You can do anything to an equation as long as you do the same thing on both sides. Now, some of you may be asking, well, why do we pick ln? Why do we use natural log? Why not log x or log base 5 or log base 7? Why do we pick ln? It's a good question. And really, it doesn't matter which one you pick here. I typically like to pick ln because ln has less things to write. There's less letters, less numbers. It's just simpler. And the nice thing about picking ln is ln will work even nicer in the next example here when we look at b. So it's not a bad idea just to use ln all the time. Now the advantage here is now we can go ahead and apply that power rule because we have the log of a x raised to an r, or in this case a 5 raised to the x minus 7. What does the power rule say? It says that we can take that x minus 7 and write it on the front. We can multiply it to the front. So what that looks like is we take x minus 7 and we multiply it by the natural log of 5. It's multiplied. In fact, just to remind yourself that it's multiplied, you can go ahead and put a little dot in there. The other side says ln of 20 still. And now things are starting to happen because keep in mind what we're trying to do for. We're trying to solve for x. We're trying to get x by itself. Now, x is definitely not by itself. This x minus 7 is multiplied by ln 5. We just start to do some simple algebra now. You know, this is multiplied by ln 5, so what's the opposite of multiplying? It's definitely dividing by the natural log of 5. Like we just talked about, if we divide this side by ln 5, we have to divide the other side by the natural log of 5. Okay, well this is nice because now we start to see some things cancel. We're getting simpler. Left-hand side, all that's left is x minus 7, and I'm going to go ahead and drop those parentheses. We don't need those anymore. It's not multiplied by anything. And the other side, we have ln of 20 divided by ln of 5. Okay, now some of you might be thinking, okay, is this equal to ln of 4? Definitely not. Definitely cannot. We haven't seen that property where you can just go ahead and divide logs like that. There's no rule that says we can do that. So you're going to have to hold back if you're feeling the urge to want to do that. We really just have one step left. Our last step here is to get x by itself. And of course, we see that it's a minus 7 next to the x, so we do the opposite. We go ahead and add 7 to both sides. And when we do that, those 7's go away. And what we're left with is x equals the natural log of 20 divided by the natural log of 5 plus 7. Now, if we go back and look at our directions, it said find the exact solution and then approximate to the nearest thousandth. That means we need to go ahead and bring our calculator into the mix here. So let's go ahead and pull that up. Let's talk about how we would enter that on our calculator and clear any result you have there. And let's type this in. So we know where our ln button is. It's right there. So we take ln of 20, close parentheses, divided by ln of 5, close parentheses, plus 7. And if you round to the nearest thousandth, we can clearly see that's 8.861. So let's go ahead and write that in. This is approximately equal to 8.861. Box up the answer. There we go. Okay, so let's look back real quick at what we did. Remember, we first isolate the exponent, and once we do that, then we can take the ln of both sides and use the power rule. And from there, it's just simple algebra. Let's see how this plays out with another example. Again, notice that here we had an exponent. Here we also have an exponent. Here the exponent's base 5. What's the base here of this exponent? Hopefully you said yourself that this is exponent base e. And we want to remember what we did first in the last example. What did we do first? We isolate first. We do the same thing over here. We always want to isolate first. So, of course, our first thing is to subtract 35s from both sides. And when we do that, we're left with 4 times e to the x minus 3 power equals 72. And you might think here that now our exponent is isolated, but really it still is not isolated because it has this 4 multiplied on front. So to undo that, of course, since this is 4 times, we would want to divide by 4. Okay. Which cancels out those 4's. They divide out, which leaves us with e to the x minus 3 equals 72 divided by 4, which is 18. Okay, so again, we isolated first. Now, well, remember what we did in the last example? We took the natural log of both sides and then we used the power rule. Well, let's try this again. Let's see how it plays out. If we take the natural log, we're left with the natural log of e to the x minus 3. Let's write that in black here. Natural log of e to the x minus 3 equals the natural log of 18. And I want to remind you of something that we learned earlier. Remember, this is a very important result, a nice shortcut. Anytime we take the natural log of e to some power, because the natural log and the e are inverse functions of each other, they kind of cancel each other out. They knock each other out, and all we're left with is x. Well, this is nice because as we look at any sort of exponent here, like natural log of e to the 5th, this just becomes 5, or natural log of e to the 7th becomes 7, or natural log of e to the x minus 3 becomes x minus 3, which is what we have here in this example. The natural log of e to the x minus 3 is just x minus 3. Well, this simplifies things a lot. It's equal to the natural log of 18. And do we have x by itself? Well, of course not. We need to do one more easy step. We need to add 3 to both sides, which does isolate the x for us. It gives us x equals the natural log of 18 plus 3. And let's go ahead and round that. Let's get an approximate answer. Plug that in our calculators. The natural log of 18 plus 3. We round the nearest thousandth. It looks like 5.89. That's how we'd solve a problem like that. If we turn over to the next page, we have an important property that can help us solve equations. It's called the one-to-one property of logarithmic functions. It says for any positive real number b, where b is not equal to 1, and it's also positive, which means it can't be negative, and if r and s are real numbers, then if r equals s, then the log of r is equal to the log of s. Now we kind of saw this in the last example. Remember, we're starting with r equals s and saying that the log of r equals the log of s. And in the last example we did that. We started with not specifically r equal to s, but we started with 5 to the x minus 7 equals 20, and we took the log of both sides. We started with e to the x minus 3 equals 18, and we took the ln of both sides. In other words, what the first part of this property says is if you start with something equal to each other, then the log of each of those things are also equal. Or in other words, you can do this, take the same log of both sides. The nice thing about that is it goes the other way too. If I have the log of r equal to the log of s, then we can assume that their arguments, the r and s, must be equal. Now, the key thing I want to point out here is that the bases, though, they have the same base. This only works if the bases are the same. So if I wanted to solve the next example, notice they're both common logarithms, log base 10. And since it's a log equal to a log, I can just drop the log and say, okay, well, that means we have x squared plus 3x minus 11 has to be equal to 9x plus 5. Which is what type of equation? It's a quadratic equation, which we haven't maybe solved one of these for a little while, but we should know how to. What do? We get everything on one side of the equation, so I could subtract the 9x over, subtract the 5 over, and end up with x squared minus 6x minus 16 equals 0, which it turns out in this case is factorable. We get x minus 8 and x plus 2 equals 0. Which gives us x minus 8 equals 0, or x plus 2 equals 0, which gives us x equals 8, and x equals negative 2. Now, one of the things you got to remember about logarithms is that I can only take the log of a positive number, even what the graph of log looks like. Remember, this is y equals log x. the domain was everything from 0 to infinity. There was this vertical asymptote here. So you can't take the log of a negative, so we need to check for extraneous answers. In this case, I can't use -2. This is extraneous. Because on the right hand side, the log of 9x plus 5 would become the log of -18 plus 5. If x is equal to -2, that's 9 times -2 is -18, which is the log of -13. You just see them verify. If you try to put that in your calculator, the log of -13, you get an error. It's not real. So we'll throw that answer out. The other one, the positive one, works out fine. So we just have x equals 8. Now the next one is a little bit different form because there's not a log on both sides. But just like in the problems at the bottom of the first page, where we converted exponential form to log form because we were stuck, we can go the opposite way here. We can convert from log form to exponential form. First, isolating the log, so adding 5 to both sides. It gives us log base 3 of 2x minus 1 is equal to 3. And we're stuck. How do we get rid of log? And one of the great things I always see students try to do is, oh, well, I can divide by log 3. I can divide by log base 3. No. We can't do that. We can't divide by log because it's not. This isn't log times 2x minus 1. It's the log of 2x minus 1. Remember, it's a function. You can't divide out functions. They're not operations. They're not operations. They're a function. So I can't just divide out the log. But what I can do here is I can change to the exponential form. This is one of the things you're just going to need to remember is that when you get stuck with logs or exponents, try changing to the other form. And so if I do that, I see the base is 3 and the power is 3, so I have 3 to the third power is equal to our argument 2x minus 1. And how easy is this to solve? 3 cubed is 27. If I add 1 to the other side, I get 28 is equal to 2x. Dividing both sides by 2, I get x equals 14. If I plug 14 back in just to be sure, 2 times 14 is 28. 28 minus 1 is 27. That's okay. So yeah, x equals 14. When you get stuck with logs or exponential equations, convert back to the other form. And most of the time that'll be how you're going to go about solving them. So let's look at this next one. Looks kind of ugly. We have 2 logs, we have number on the other side. Well, this is why we did the previous section where we talked about the properties. Remember, we learned about the product rule and the quotient rule and the power rule. The product rule allows me to rewrite this left-hand side as a single logarithm where we take our arguments. We take our arguments of x and x plus 18 and we do what with them? We multiply them. Remember that? Product rule. And now this problem looks basically exactly like the one we had on the last page. Last page we had a log equal to a number, so what did we do? We changed it to exponential form. We change it to, well, our base is 3, our power is 5, it should be equal to x times x plus 18. What's 3 to the 5th power? 3 to the 5th power is 243. So 243 is equal to x squared plus 18x, which is another quadratic, so we get everything on one side. X squared plus 18x minus 243 equals this is factorable. We have x plus 27 times x minus 9 same way we've solved quadratics all along. Gives us two answers. It gives us the x equals negative 27 or x equals positive 9. And we can see one of these answers obviously won't work. The negative 27, I can't take the log of a negative 27, so my answer is going to be just x equals 9. You could also apply the quotient rule to the other side. This example is going to be the log base 4, where we take the quotient of the two arguments, 7x minus 1 over x minus 4 is equal to 2. This is an application of the quotient rule. And again, we're now kind of stuck. We have a log equal to a number, so what do? Change it to exponential form. The base is 4, the power is 2. Base 4, power 2 equals the argument. Or 16 is equal to 7x minus 1 over x minus 4. How do we solve something like this? Well, it's an equation with a fraction. Multiply by the least common denominator. Multiply this side by least common denominator. When I distribute that, I get 16x minus 64 equals 7x minus 1, which gives us 9x equals 63, or x equals 7. Skip some steps there. I got all the x's on this side, so when you subtract 7x, you get 9x. When you add 64 to this side, you get positive 63, and then we divide by 9 to get 7. 7 an okay answer. It looks like when I plug 7 over here, I get 48, which works. If I plug 7 in here, I get 3, so that both of those are positive inputs into the log, positive arguments. Then, of course, the last thing we could do here is we could find inverse functions, and we have logarithmic functions. Okay, so the last type of function that we have is how we go ahead and find logarithmic. Okay, so the last thing we're going to do here is talk about how to find inverse functions. We've done this before, and we know that logarithmic and exponential functions are inverses of each other. Let's see an example of how this works using the steps that we learned in the last chapter. Remember, our first step is to let f of x equal y. So we have y equals e to the x plus 1 minus 7. And then once we've done that, we can switch the x's and the y's, so x equals e to the y plus 1 minus 7. And then we want to try to solve for y. So we add the 7 to the other side, we get x plus 7 equals e to the y. And now what? Now we're stuck. We're in exponential form and we're stuck, so we turn to log form. Or we can try that little trick of taking the ln of both sides. Remember, we can take the ln and the ln of this side, which gives us the ln of x plus 7 equals the ln of y plus 1. Excuse me, the ln of e to the y plus 1. And remember, what happens over here is the ln and the e cancel, and we just get y plus 1. Here we have ln of x plus 7. Or you could have just, if you could take the ln of both sides, or you could talk about just converting the other way. Remember, this is log, the base is e, the power is, or the argument is x plus 7, and it should be equal to the power of y plus 1, which is the same thing as we have over here, because log base e is ln. And finally, ln of x plus 7 minus 1 is equal to y, which means our inverse function has now been found. It's the ln of x plus 7 minus 1. And that does it for this section. Thank you for your time. We'll see you in class.